We're going to look at 5.2. We're going to talk about probability rules. Or you could say probability rules. No? Alright. Alright, so first thing we got to do is talk about some definitions. We're going to talk about our sample space. And a lot of times it's going to be good for us to write down or really imagine the entire sample space before we calculate some probabilities. The sample space is all of the possible outcomes. And then, in your book, there's also a definition of a probability model. It says it's a description of some chance process that consists of two parts, sample space and a probability for each outcome. We're going to get into that in more detail. Don't really need to write that down on this point. So we're actually going to just go right into it. We're going to talk about, we're going to write down a sample space immediately, or actually a couple of them, right? So, the one that your book gives is rolling a die, and it's the best one, honestly. So if you're rolling two dice, right? One die is green, and one die is, then you say one die is orange. And the idea is that you have to be able to differentiate between the two dice, right? So the sample space for rolling two dice. So all of your possible outcomes, if you were to roll two different dice. That's really what we're looking at, right? And the reason why they differentiate between orange and green is because you can actually get two different things, right? So, and I'll explain it here in a minute. So I'm actually going to have to do this in color. So I'm going to have to grab different colors. So it's going to be weird, but I will do black and red, I guess. So I could get a 1 and a 1, right? I could get a 2. And you can see how this is actually going to work, right? We're going to say first die, I'm probably going to need a little more space. We're going to get all the possibilities for our first die, right? 2, 3. Sorry that I'm not good at drawing. 4, 5, and then 6. Right? So if we were to roll two dice, I have all the possibilities for my first die. All right, so we'll go ahead and list all of the combinations where my first die comes up as all these different things, and our second die is always 1. There it is. Yeah. All right, we can actually write out this whole sample space by continuing this pattern, right? And it's a good way to do it, right? We'll write out the pattern. The first die turns out to be 1, 2, 3, 4, 5, and 6. Then our second die is 2. Do you see how this captures every single combination of outcomes in the sample space? We continue going through this, and we're going to actually refer back to this picture when we calculate some simple probabilities of dice. Does anybody know anything about the game of craps?
Oh, craps.
Huh? It is a dice game. Oh no, that's cribbage.
Cribbage is fun.
Cribbage is a really cool game.
I love
I'm gonna run out of space for my sample space. Hopefully not. I just think it's a good exercise. This sample space is written in your book, but I think it's a real good exercise to write the entire sample space. We'll do a couple of them just to get the idea. Oops. Word, not like that. No, we're like that. I know it's just time consuming and weird, but it's worth it. Okay? Yeah, we gotta write every single one. Yeah, we have 2 more rows. 2 more sets of rows, or columns, I should say. We have 12. And again, I know this seems tedious and time consuming, but it's really nice to see it, to draw it, to touch it. You could look at a picture of it, and I don't feel it's as meaningful as when you actually create it. And the cool thing about the video, if I was doing this with a flip class, you would be able to fast forward.
easy.
Or just pause it and write it down yourself, right? And the last one.
I'm gonna do hard work.
Beautiful, I did it. Whew.
6x1.
This is my masterpiece.
6x4.
Huh?
6x4.
You're 6 by 12? Cool. But, hold on. Half that, right?
Yeah.
Because each set of 2 is 1 outcome, right? So there are 36 total outcomes. So our sample space has 36 possible outcomes. And we're going to refer back to this. We're going to answer a couple of simple probability questions using this. But a lot of times, honestly, with like something that would be considered a more simple probability question, this is the spot that you get tripped up at. It's actually envisioning or drawing the sample space. Some people, it's very intuitive and they see it in their minds, and some people have to write it out, and that's okay. It's all right. So we're going to define an event then. So here's our sample space for rolling dice, and we're going to go ahead and actually first define what probability is. So we say that the probability of event A occurring can be written like this, or be expressed. We're using this. We're going to use this one. Form U. We're going to call it. We're going to say the probability of A. That's how we say that. Okay. So it's not P of A in this case, like you would say it like if you were in a class that was algebraic in nature, right? You would call that P of A. It looks like function notation. We're not going to say that. We're going to say the probability of A. So if you have P and something in parentheses afterwards, that's we're going to be talking about the probability of event A or whatever, okay, or whatever's going on with that, okay. So that's going to be the number of outcomes. I like to call it. I like the way when I express this in class, I'll talk about it as a success, right? If you want event A to occur, right, you would have your numerator of this be the number of successes, the number of events that corresponded to event A. I'm gonna we're gonna call it number of outcomes, right? In event A, that are event A, over our total possible outcomes. And that's pretty simple. I'm sure you guys have all seen that before. You get that, right? We worked with stuff like that before. We expressed our probabilities as some ratio or as some proportion, right? All right. So with that said, then, what then? And I heard it said already. What then would be the probability of any single event occurring within this particular sample space? So you say each one of these, so one event in this case, right? So that's one event, right? That's one event. That's one event, right? Because we're saying, hey, you roll the black die and the red die, right? So each one of those is a single event. So the total number of events that could occur, our possible outcomes in our sample space are 36, right? And so the probability of any single event occurring would be 1 out of 36. Yeah? Okay. So for the die, so for the dice, if A is any single event occurring probability of A is going to be equal to 1 out of 36, right? Okay. A couple more rules, and then we're gonna work with the sample set and kind of get an idea of just calculating some basic probabilities. Okay. So our next definition would be the complement. So we have a complement. The complement. Right? So the complement is the probability that event A does not occur. Okay. And we've actually been dealing with the complement quite a bit, especially when we were doing when we were calculating normal probabilities, right, or proportions using a normal distribution, right? We would wind up subtracting from 1 in order to get, so if we wanted something shaded, an area shaded on the right hand side, right, and we would go to our table and it only gave us the area shaded on the left hand side, we would subtract from 1. We're actually taking the complement. So I'll finish this. The complement is the probability that event A that event A does not occur. It can also be noted as A with C in the superscript. That's A complement, or the complement of A. Right? You could also say that means not A. Okay? And kind of say the next thing that we need is to talk about events that are mutually exclusive or disjoint. Okay. All right, so if we have two events, A and B, and I wonder, I'm going to go ahead and use the actual word and, so we don't mess up notation. They're mutually exclusive. They have no outcome. Okay? And a lot of times you'll hear this term used, and also another definition, I should have put it right over here, but another way to call this, another nomenclature for this, is to say that it is disjoint. Okay? So those two things are interchangeable. Okay? The word disjoint and the word mutually exclusive mean the exact same thing, and they can be both used in the same way. So you'll hear people use the term mutually exclusive to describe a lot of things, right? But definitely not in terms of probability. All right, so another or simple example of mutually exclusive events would be like, hey, what if none of us sorry, everyone in this room that had a dog as a pet did not have a cat, right? And every single person in this room that had cats as pets did not have dogs. Then those two events are then mutually exclusive because there are no students that have both cats and dogs. So really, for some reason, cats and dogs always come up with the explanation of mutually exclusive events. Probably because it's the most PC thing to say. All right. So there's that. All right. So now let's get down to business. I'm gonna just go ahead and write down some notation stuff, and then we're gonna work with this sample space that we have already created. So again, with the complement rule. So now we're going to take these definitions and we're going to actually get some notation and equations that we can use, right? So this says the probability of A complement, or not A, right, is going to be equal to 1 minus the probability of A. And we have another rule. We have an addition rule. But this only applies to mutually exclusive events. And it tells us that if we have the probability of A or B, what we'll do is we'll be able to add the probability of A plus the probability of B. And we're going to go ahead and use that right now. Fantastic. Let's go ahead and use each of these. So let's go back to our sample space here. Whoops, I was there. Okay. And we keep fantastic. All right. So I'm not going to ask you a simple question. I'm going to ask you which number or number values, right, are the most likely to occur in this sample space. What's the most likely to occur? We're looking for the number value that's occurring the most often. Because, as we just defined, right, our probability is going to be a success, or a number of successes, or a number of outcomes, divided by our number in our sample space. So, if that numerator is smaller, we're going to wind up with a lower probability. But if that numerator is larger, we wind up with a larger proportion or probability, right? All right, so the first thing I asked, though, was that we look at the greatest probability. So if we look, we see how many different combinations of 7. There's one. Okay, there's one. It's kind of fun to see the pattern that emerges from it too. I don't know why. Those things make me feel good for some reason. Look at that. There's all of our combinations that create 7. So we have a 6 in 36 chance, or our probability of 7. So we're going to actually use our notation. So, and I'm actually going to make sure that get rid of this first. Here's a way you can So this is the way we would write a probability. We would define the event A as you roll 2 dice. And the total is 7. Alright? So probability A is you roll 2 dice. So then we can say that I was about to write f of A. The probability of A then is going to be 6 out of 36, which is the same thing as 1/6. And we would love to express that proportion as a decimal. So approximately 0.16. Let's just round there, okay? Right, and I had to round, and so I definitely have to use that approximate symbol. Right. Cool, let's look at another event. And really, today, we're just getting used to using notation, right? These are all things that I think probably most of you have calculated at some point in time in school. A lot of people have. Some people haven't. But the notation is quite possibly very neat. So, let's go in and look at another one. I think there's another one that's very likely to occur. Let's see. What is the probability of getting 11?
Lower. 5 and 6.
So we got, my dots are awful, but we got one here. And we've got one here. I've done circle 10. How about? And that's it, right? There are only 2 possible outcomes that will result in us getting 11. So we could write that as if B is the probability that you roll 2 dice and the total is 11, then the probability of B is going to be 2 out of 36, or 118, which is approximately 0.056. All right. So, hey, now we have 2 probabilities. We can play with some of these rules, right? Huh? So let's look at that. So if you don't want a 7 most of the time, right? Say we're comparing the game of craps. Your book doesn't do that because gambling is illegal in most cases, unless you're on native land or in Las Vegas. But other than that, it's illegal. So the book doesn't talk about gambling or the craps very much, but I like to relate it to craps because let's look at the other idea, right? So you don't want to get a 7, right? Okay, what's the probability that you don't get a 7? So what we're looking at then is the probability of not A or A complement. Well, that's going to be 1 minus 636. Well, we could just subtract that from 1 as well, right? But I would like to actually get an exact answer first. So that's going to be 30 out of 36, right? We're essentially subtracting those 6 possibilities from my entire sample space, right? You know what I'm saying? Cool. Works. Huh? So I mean, that's not bad, right? The probability that you don't get a 7. You can kind of mess with people's minds like that, right?
Sure.
Yeah, right? The probability that you don't get a 7 is pretty high. But in all reality, the probability that you get a 7 is higher than the probability that you get an 8. And that's why the game of craps is a mental game that is being played on the player by the house. The reason why casinos make a lot of money is because the games are set up so that they win more often than they lose. It's just the way it's made, right? Otherwise, they would have to give money away all the time, and that's just not a good business plan. So in the game of craps, right, you'll bet that you get an 8 before the roller gets a 7, right? And if you look at that and say, well, you know, the probability that they don't get a 7 is around 83%. Awesome. That's working so good in my favor. But the problem is the probability of rolling an 8 is quite low. So it's actually lower than the probability of rolling a 7. So that's the way that the house is rigged the game. That's using these probability ideas. And our last one is, what would be our probability of rolling a 7 or an 11? So what's the probability of A or B? So we have to ask ourselves, are these 2 events mutually exclusive? Do they have any events in common? Is it possible for me to roll a 7 at the same time as I roll an 11? No, because each roll is definitely a mutually exclusive event. It can't be 2 numbers at once. It's either 11 or it's 7, right? So in that case, we can use our rule that tells us that that's the probability of A plus the probability of B, which would be 1/18 plus 1/6,
Yeah, see? Get out.
which is approximately
223.
0.223. So now that changes the game as well, right? If the probability, if you're trying to roll a certain number before you roll a 7 or an 11, now your chances of actually getting that number just really, really, really plummeted. The chances of getting a 7 or an 11. Yeah, yeah. No, I'm saying, so if Oh yeah, of anything other. Yeah, that also. Yeah, it decreases your chances of. Yeah, so the probability of A or B complement, right? Yeah, that's what you're saying, right? Well, cool guys. Thank you so much. We'll keep talking about this again next time. Dormant out. I just dropped the pen, but you can't see it.